All right, let's dive into a really powerful tool in Java, abstract classes and methods. If you've ever found yourself wishing you could just set the rules for a big project, well, this is for you.
So, have you ever been in that spot, maybe on a team project, and you're just thinking, man, I wish I could create a master template, some kind of guide that every other developer has to follow, a way to make sure certain features get built even if you don't know the nitty-gritty details yet? Well, guess what? You totally can.
The whole concept that makes this possible is a core idea in programming called abstraction. And really, it's all about one thing: hiding the messy details so you can focus on what's actually important.
Okay, so what is abstraction really? It's basically the principle of hiding all the complex, behind-the-scenes stuff and only showing the parts a user needs to interact with. The whole key is to focus on what an object does, not how it does it.
Just think about a car, right? When you're the driver, your world is pretty simple. You got a steering wheel, a gas pedal, a brake. You know what they do. You don't need to understand the combustion cycle or some super complex algorithm for the anti-lock brakes just to drive to the store. All that stuff, that's the hidden implementation. And that separation, that's abstraction in a nutshell.
So that's the big idea. But how do we actually use this in our code? Well, Java gives us a very specific tool for creating these high-level designs.
And that tool is the abstract class. Honestly, the absolute best way to think about this is like it's a master blueprint for other classes to copy. But here's the kicker. It's an incomplete blueprint. And that's not a bug, it's a feature. That's what makes it so powerful. Just look at the structure here. You can see an abstract class is kind of a hybrid, right? It can have all the normal stuff: fields for storing data, constructors, and what we call concrete methods, methods that are fully written out. But it also has these special empty methods called abstract methods. These are the parts of the blueprint that are left blank on purpose for someone else to fill in later. Now, like any cool, powerful tool, these incomplete blueprints come with a few golden rules. You've got to follow them to use these things correctly. And here is rule number one, the big one. You can never create an object directly from an abstract class. If you try to write new animal, you're going to get an error. And why is that? Well, think about it. The blueprint is incomplete. It's got those empty, undefined methods. This slide really nails the logic behind that rule. I mean, if you could create an object from that incomplete shape blueprint, what on earth would happen when you tried to call the area method? There's no code there. It wouldn't know what to do. So Java is smart about this. It stops you right in your tracks and prevents that error before your program even tries to run.
All right, so a few other key rules to keep in mind. First, like we saw, these abstract classes can be a mix of fully coded methods and empty abstract ones. But here's the really important part. For any class that inherits from it, that new class, the subclass, must provide the code for all of the abstract methods. It has to fill in all the blanks. If it misses even one, then it's still considered incomplete, and guess what? That subclass has to be declared abstract too. Okay, let's zoom in on those empty methods themselves for a second. They're not just blank spaces in your code. They represent something much, much bigger, an unbreakable contract. See, an abstract method is really a promise. When we put public abstract double area into our shape blueprint, we're making a guarantee. We're saying, hey, every single concrete shape that uses this blueprint will, without a doubt, have a way to calculate its area. We're defining the what, but we're leaving the how up to the specific shapes down the line. And right here, we see that promise being fulfilled. A concrete class, Circle, comes along and uses that @override annotation, which is basically its way of saying, hey, I'm providing the implementation you asked for. It gives the specific formula, the how, for a circle's area. The contract laid out by the blueprint has now been honored.
All right, enough with the theory, right? Let's see how all these pieces, the blueprint, the rules, that unbreakable contract, all come together in a real, practical example. So here's our setup. Up top, we've got our abstract shape blueprint. It says that any real shape has to have a way to calculate its area and its perimeter. Then, underneath, you see our concrete classes: circle, rectangle, and triangle. Each one of them follows the blueprint and provides its own unique formulas to fulfill that contract.
Now, because all these different classes share the same shape blueprint, we get to unlock one of the coolest features in programming: polymorphism. What this means is we can do something amazing. We can create a single list that holds shape objects, but we can fill it with all sorts of different actual objects. A circle, a rectangle, a triangle. They're all different, but our code can treat them all as if they're just shapes.
So, what actually happens when we loop through this list and call a method on each item? This is where the magic really is. So, step 1, our code calls a shared method. Then inside that, step 2, it calls the abstract area method. Now here's the cool part. At the exact moment the code is running, the Java Virtual Machine, the JVM, checks the actual type of the object. It asks, okay, what am I really looking at here? Is this a circle or is it a rectangle? And then boom, step 4, it sends the call to the correct, specific version of the area method. This whole process is called dynamic dispatch, and it's what makes our code so incredibly powerful and flexible.
So what's the big payoff for all this? Well, our code ends up being super clean and incredibly flexible. We can handle all our different shapes in this one uniform way, but each one still does its own thing correctly. And it's all thanks to that master blueprint we created, enforcing a common structure from the start.
Ultimately, that's what abstract classes give you, the power to define a contract, a master plan for your software. They force consistency where it matters, but they still allow for all the unique, flexible details where you need them. You're not just banging out code anymore. You're actually designing the architecture. So the only real question left is, now that you can design the blueprint, what kind of powerful systems are you going to build?